Hey, this is going to be a short lecture on the pendulum, measuring the acceleration due to gravity due to a simple pendulum, using a simple pendulum, okay? And this is the work of Galileo, okay? Before we get to that, again, we want to measure G, right? G is the acceleration due to gravity, acceleration due to gravity. It's not gravity, it's the acceleration due to gravity. Okay, and on Earth and in lab, the number that we're gonna want to get is this. G is 9.8 meters per second squared. And we're going to review this number. We're going to review this, okay? And this is the number we're always going to use in lab, okay? Now, for our exam, so in class, and for all our quizzes and exams, okay, not counting lab quizzes, okay, but for our exams, we're going to take G, we're going to approximate it so we can do calculations much quicker to be approximately 10 meters per second squared, okay? We're going to approximate the 9.8 with 10, but in lab, we're going to use this number, okay? And G really is in essence just a measure of how much the Earth's gravitational pull is pulling on this. So this number represents that. Now, if we lived on a larger planet, something like Jupiter, which has much more mass, then G, the acceleration due to gravity, which is, again, measuring the gravitational attraction of the planet in this case, would be much, much bigger than 9.8, maybe 10 times or 100 times bigger. On something like the moon, which has less mass than the Earth, G, the acceleration due to gravity on the moon, is less than it is on Earth. In fact, it's about 1/6 as small, okay? So G depends on what planet you're on, or what asteroid, or what's pulling you, okay? On Earth, G is 9.8 meters per second squared, the number we'll use in lab. Okay, now before we get to the experiment, let's do some background. Okay, let's just do a little background review. Okay, this can't hurt. Okay. Okay. So if I say I'm moving at 30 meters per second, no, let's do 30 miles per hour. And I travel for 5 hours, 30 miles per hour for 5 hours, I know I've traveled 150 miles. So my distance, D will be my distance, is what? It's how fast we go. What did we say? We said 30 miles per hour. Per means divided by. And now we're going to travel for, what did I say? 5 hours? 5 hours. I'm going to put HR. Okay. And what we end up with, notice the time goes out, hour divided by hour just cancels out, and we're left with just miles. Well, miles is a distance. Well, I want my answer to be a distance, right? So 5 times 30 is clearly 150 miles. Simple, simple, simple. Okay. So if we call this, and again, we will differentiate between velocity and speed later on, but for now, we'll just call this the velocity. I'll call it V, and the time is T, then V times T is equal to the distance, okay? Now V, if we solve this for V, we just rearrange, divide both sides by T, right? If we divide both sides by T, the T's cancel out here. And I have V is just equal to distance over time. Okay. Well, again, we just used distance was miles and time was hours. So we get miles per hour. You see the units. So V has units of a distance divided by a time. And so it could be centimeters per second. It could be miles per year. Any distance over any time would be the units of a speed or a velocity. Okay. Now, actually, if we call the distance, just call distance, let it be x because it looks fancier, okay? We really want that v is a change in distance. Delta is change in, right? You should all know that, change in. Delta x is a change in distance over, we could put a change in time. If the distance doesn't change, if delta x, if you don't change your distance, then your speed or velocity is zero, okay? Very simple. Okay, so let's go back to here and say d equals vt. Okay, now we're going to use meters. Distance, we're going to be using meters. Okay, and t, we're going to be using seconds. Okay, so d on this side, the answer should have meters. I'm just going to write meters. Okay, we just said v was a distance over a time. Well, distance is meters. And time, we said, is in seconds. Now, when we multiply that by time, which was seconds, we see the seconds go out, and I'm left with meters. So meters and meters. You must have the same units on each side of the equation. Otherwise, it makes no sense. The old expression, you cannot add apples and bananas. You have to have the same units on each side. Okay. Now, I want you to notice something about this. This says if I travel at whatever, 30 miles per hour for 5 hours or whatever. But we know that the speed or velocity, v, can change, right? It doesn't have to be a constant. So if I have a delta v, a change in v over a change in time, well, remember, delta is just a word, just change in, has no units. So this thing would have units of v, but v we said was meters per second. And now we're dividing by a delta t, so now we have to divide by seconds. And to simplify this is just written as meters per second squared. Okay, and this object, the change in velocity with change in time, is what we call a, or acceleration. Okay, so acceleration is going to have units of meters per second squared. Okay, now let's see, go back, let's write this, go back to our distance formula. How far we go depends on how fast we're going, v, times the time we travel. That's good, right? And we said, again, this is in meters. And this is meters per second. And this, we said, was seconds. So again, the seconds go out, and we're left with meters equals meters. Now, what happens if we accelerate? Well, if we accelerate, our distance is going to change. So I'm going to put an A here. Okay. Now, A, we just said from up here, A, acceleration, has units of meters per second squared. Look at that, second squared. Now, remember, we need to have just meters, right? Because we need to have a distance. The right side should have the same units as the left side of this equation. Now, if I have meters per second squared, how can I get rid of this second squared? Because I just want meters. And the answer is if we multiply by t squared. Remember, t is in seconds, so t squared then would be seconds squared. And there we have it, seconds squared. Now the seconds squared go out, and I'm left with meters. Okay, now I have to give a fudge factor. Okay, that we derive this when we take a real physics class, and if we were doing real physics, I would derive this factor. But for us, for now, I'm just going to tell you there's a factor of 1/2 here. Okay, that's all you need to know. So our formula for distance is v times t plus 1/2 at squared. Okay, now we're going to come back to this in 1 second. Okay, as I said, this is a background for the lab, just a little discussion that we can all use, a little review. Okay, now remember, v is how the change in distance with time, and a is the acceleration of an object, means that the velocity changes with time. So suppose I have an object, I'll take a ball and we're going to drop it. Okay, if we drop it, and I'm going to call this v0, okay, that's the initial speed, okay? Speed. Okay, now if we drop something, that means the initial speed is 0, right? We're dropping it. Okay, now if I drop an object, right here, the speed v0 equals 0. 1 second later, it's accelerating because of g. Now, just for illustration purposes, I'm going to take g to be 10 meters per second squared, just to show you, okay? Now, what does this number mean? This number means if I drop an object, the speed changes by 10 meters per second every second, okay? We're using 10. So every second this object's dropping, the speed is going to increase by 10 meters per second. So if we start with an initial speed of 0, right, it's 0 here, in 1 second, the speed then changes by 10 meters per second. So the speed is 10 meters per second. In 2 seconds, then, the speed increases again by 10 meters per second. So now the speed is 20 meters per second. And you get the idea. In 6 seconds, the speed keeps increasing every second by 10 meters per second. So in 6 seconds, the object is moving at 60 meters per second. Okay, that's what we mean by g. Really, it's 9.8, but we're approximating. Okay, by the same token, and we'll do more of this in class, if I throw an object up, okay, if I throw an object up, every second, so suppose I throw an object up at 80 meters per second, that's my v0. Now remember, g is slowing it down. G is acting down, right? Because this is the Earth. Okay, so in 1 second, the object hasn't sped up by 10 meters per second. It's slowed down by 10 meters per second. So in 1 second, this object is moving at 70 meters per second. In 2 seconds, the object's moving at 60 meters per second, because every second, the object's slowing down by 10 meters per second every second. Okay, so now we have an idea about what g is. Okay. And again, we'll do this in class some more. Okay, so now we want to talk about Galileo's experiment. Galileo, right? And he wanted to measure g. And that's what we're going to do is his method, measure g. And remember the number we want to get. We want to get 9.8 meters per second squared. Okay, 9.8. That's going to be our lab number. Remember, this is what we use in lab and all the lab quizzes. Okay, lab. Don't forget. Class, we're going to use 10 meters per second squared for the acceleration due to gravity. Okay, and his method is going to be what's called a simple pendulum. Okay, simple pendulum. Okay, so let's look at our simple pendulum. Okay, I'll put something here for now. Okay, now here's the pendulum. Okay. All right. The pendulum has a length L. So L is the length of the pendulum. And just so you know, when you actually do the experiment in lab, okay, the length of the pendulum, oops, sorry, my pen stopped working for a second. Okay. Pendulum, okay, we have to measure this to the middle of the mass. Okay? So we're going to measure it right to the mill. This is M. And this mass, the mass for a pendulum, I don't know why it's called this, is called the bob. They could call it Robert, but okay, so it's called the bob. So this is called the bob, okay? And there's the length of the pendulum measured to the middle of this mass, or middle to the ball, okay? Now, we're gonna, if I just draw a straight line straight down, okay, and say there's an angle, measure this angle theta. This theta, right, it's a theta, okay, it doesn't matter what we call, essentially measures how far back we pull the pendulum. So theta is called the amplitude of oscillation. Amplitude of oscillation. Okay, the farther back we pull it back here, then we get a bigger theta, right? That would be theta. Okay. Okay, pen failed. Okay, so that would be theta, a bigger, larger theta. So that's going to measure the amplitude of the oscillation. Okay. The other thing we're going to need to know is this. If we say we pull the pendulum to right here and we let it go, well, what's going to happen is the pendulum's going to swing. Whee! Oops, my pen swung the wrong way. It's going to swing over to this side. And of course, it'll be a little smaller than theta because the air resistance is pulling it back, but I'm trying to draw. Oops, my pen does not want to draw right. All right, so here it goes. So here's the M here. M. Okay, so it's going to swing to there, wee, and then it's going to swing back, wee. The time it takes the pendulum to go from one end and then swing back is called the period. So T is called the period of oscillation. Of oscillation. And it's going to be measured in seconds, right? 1 second, a half a second, 0.37 seconds, oscillation. Okay, so again, the period T is the time it takes the pendulum to swing from one end to the other and then back again. That's one period, okay? And it's going to be measured in seconds because it's a time. And the question is, well, why? Why does this pendulum fall? Why does it fall? Well, the reason it falls is because it's being pulled down by gravity, so it's pulling away. See, if it was just laying here, nothing would happen if it was just laying there because gravity would pull it down. But here, it's going to pull it, go there, and then gravity's going to pull it back. Okay, so the period T depends on G. If there was no gravity, this pendulum wouldn't move. Okay, so Galileo realized that the pendulum's period depends on G, and it's going to depend on L. So now I'm going to write the formula that Galileo came up with, okay? Okay, Galileo came up with the formula for T. So the period of this simple pendulum is given by 2 pi. Why the heck is there a pi? Well, if we look at this, I'll do this here on the side. If we look at a little picture, okay, this is our pendulum, a little picture, right? If we look at it, we let it swing all the way around, right? You could see it would swing in a circle. We know circles always have pi's in them, and going around is a 2 pi. So this doesn't make too much. It's not too surprising there's a 2 pi. Okay, and then we have a square root of the length of the pendulum divided by G. Okay, now let's look at L over G. L over G. Just let's look at the units for a second. Well, L we want in meters. Remember, G is meters per second squared. Seconds squared. Now, meters goes out with meters, and the seconds squared comes up. So this has units of seconds squared. So if we take the square root of L over G, we get the square root of seconds squared. I'm just looking at units, right? Which is just seconds. So that makes sense because t should be in seconds. Remember, 2 pi has no units. Okay. Now remember, g is equal to 9.8. This is what we want to get, meters per second squared. If we convert this to centimeters, then this would be 980 centimeters per second squared. Okay. And if we wanted to divide G divided by L and we wanted to do things in centimeters, well, the same thing works. G divided by L would be 980 centimeters per second squared. Oh, I mean L divided by G. Oopsie, sorry. Divided by G. Sorry. Divided by centimeters. Oh, let's redo this. So we have L divided by G, okay, is centimeters divided by, again, well, we could put 980 if we want, centimeters per second squared. But again, if I'm just looking at the units, you see the centimeters go out. So it doesn't matter what units you use for G or for L, as long as they have the same units, okay? And this, again, is just seconds squared, okay? So for example, if we measure L is, and I'll make this up, 84 centimeters, right? And we want to know what's the period. Well, there's 2 ways we can do it, and I'll let you work out the math, right? Now remember, 84 centimeters is the same as 0.84 meters, okay? So the period, if we do it in meters, is this, 2 pi times the square root of, what did I say, 0.84 meters divided by, now we're using meters, so G is 9.8 meters per second squared, okay? And that'll give you a certain number. I'm not going to do it. I'll let you do it, okay? Now, if we want to do G and the length in centimeters, then the period T is equal to 2, oopsie, again, my pen went away. And here we go, 2 pi times the square root of, what did I say, 84 centimeters divided by G in centimeters is 980 centimeters per second squared. Okay, and this number, whatever I get, has to be, it's the same number. Doesn't matter if you do G in centimeters or meters, L in centimeters or meters, as long as they both have the same units. So we get the same number. It doesn't matter. Okay, and we'll come back to this, okay, in a bit. The other thing I want to say, because we're going to talk about reaction time, and I'll get back to this also. Well, let's stay with this, and I'll talk about reaction time. So now we have T equals 2 pi L over G, square root, okay? Remember, the whole idea is to measure, right? Our lab, we want to measure G. That's what we want to do. So that means this equation, we need to solve for G. Okay. Now everybody remembers square root, right? Square root of, oopsie, come on, pen, come on. Square root of 25 is 5, right? So if I square both sides, the square undoes the square root, so we just get 25 equals 25. That's fine, okay? So if we want to undo a square root, we have to square both sides. So we're going to square both sides. Okay, whatever I do to one side of an equation, I have to do to the other side, right? So on the left, t, when you square it, you get t squared. On the right, when you square 2, you get 4. When you square pi, you get pi squared. When you square the square root, you just get L divided by G. Okay? Remember, we want to solve for G. Okay, so I got to get rid of this G on the denominator. So I'm going to multiply both sides by G. Multiply both sides by G. Okay, so here on the right side, G goes out. So here we have G T squared equals 4 pi squared L. But I want G all by itself, so I need to divide by T squared. Get rid of that on that side and divide by T squared on this side, okay? Goes out on this side. And so we have, finally, that G is equal to 4 pi squared L divided by T squared. Now, I think in the write-up, they tell us, they work out in the table that 4 pi squared is equal to 39.44, I think. Okay, so now we have G equals 39.44 L divided by T squared. Okay, so now we have an expression. Remember, this answer, whatever we put in our numbers, should be as close as we can to 9.8 meters per second squared. Right? L is in meters, T is in seconds, so we get meters per second squared. Okay? Now, we can measure L. I'll write that down here. We can measure L. We use a ruler. Measure L. Remember, we have to measure it to the middle of the ball. So again, if our pendulum is just hanging down here, and there's our bob, our mass, M, and next to it we have a ruler. Okay. Okay, we'd measure from here right to, and we have to eyeball this, right to the middle of the ball, right? And this would be L. Okay, so we know L. L is easy. Just use a ruler. Now, what about, now we need to measure T. Okay, well, T was the period, right, for one oscillation when it goes from here and then goes to there and then goes back. So it goes there and back. That's the period T. Okay. Now, how are we going to do this? We're going to do this with a stopwatch, right? We're going to measure T with a stopwatch or your phone. Okay. Either one is stopwatch. Okay. And when somebody says start or whatever, and then stop, you see, when we start, there's going to be a delay. This delay, and the same when the person says stop, there'll be a slight delay. Why is there a delay? Because that's called your reaction time. Right? You don't react instantly. So there's going to be a fraction of a second. Let's say your reaction time, let's just say the reaction time T is, just say it's 0.2 of a second. Okay? So when you start, there'll be a 0.2 of a second delay. And when you stop, there'll be a 0.2 second delay. So 0.2 plus 0.2 would be a 0.4 second error or delay. It's really an error. Okay. Now, if the period, let's say it goes back and forth, it's not going to take much time. Let's just say it's 1.2 T equals, just making this a 1.2 seconds. Okay. Well, if there's a 0.4 second delay or error, well, 0.4 divided by 1.2 is about a 33% error. So how can we get a good measurement, right? This is equal to 1/3, right? It's about 1/3, which is 33%. So this is the amount of error just because of this silly reaction time. So if there's a 33% error in measuring T, then I'm going to have a nice error when we try to get G. So how can we get around this reaction time? What can we do? Because we still have a reaction time error. Well, what we do is we do not count only one. We don't do one oscillation, right? Remember, one oscillation, oopsie, should take about 1.2 seconds. I'm making this a one oscillation. Okay. One oscillation, 1.2 seconds compared to 0.4 seconds, we said that's like 1/3 or 3 to 1, right? That's not good. So what we do is instead of one oscillation, we let the pendulum go back and forth. Watch this. We let the pendulum go back and forth. One, right? We do this 30 oscillations. We do 30 oscillations, and we get the time for 30 oscillations. I'm going to make this number easy because I'm not that smart. Let's say the time to go back and forth. Ready, go. 1, 2, 3, 4, 5, 28, 29, 30. Okay. And then what we do is we get the time for 30 oscillations. Let's say the time, I'm making this up, is 90 seconds. That's how long it took for 30 oscillations. So how long does one oscillation? Well, T, the period for one oscillation is 90 divided by 30 because it was 30 oscillations. So it would be 3 seconds. Notice if this is 90 and your reaction time was 0.4 seconds, that the percent error is very small now because 0.4 compared to 90 is very small. So now we don't have to worry about our reaction time error, but we still got the period. We did 30 oscillations, and then we divided that time by 30, and we got what the period for one oscillation was, minimizing the reaction time error. Okay, so now, remember, we have T, oops, sorry, G was equal to 39.44 L divided by T squared, right? And if we want G in meters per second squared, we need L has to be in meters. Okay, so don't forget to convert. Don't forget to convert. That if you measure the length to be 73 centimeters, don't put 73 in there. That's wrong. You have to make this into 0.73 meters. If you keep it in centimeters, then your answer G will be in centimeters per second squared. And then the answer, if you want the answer with G in centimeters, then the answer should be 980 centimeters per second squared. Okay. Otherwise, this number, if we use meters, should be 9.8 meters per second squared. So we measure L using that ruler to the middle of the mass, the bob, and then we measure the period T for 30 oscillations. Well, we measure the time for 30 oscillations, divide by 30, and then we have the period T, and then we square it, and we divide the length by T squared. Just put in those numbers, then multiply by this. Remember, this was 4 pi squared. We derived that up top. And this number should be something close to 9.8. Okay, and that's the lab. Okay, the second part, very quickly, the reaction time. What we do, and remember, you got to try to surprise the person because if they're waiting, nothing's going to happen. So here's a person, right? And they're going to hold out their hand, right? And you're going to be here, okay? And you're going to hold a ruler. Okay, I'm sorry, it's a terrible picture. Okay, and then you have to distract, little beautiful Susie or Joe or whatever. Say, "Ooh, you look so pretty today," or "I like your dress," whatever it is, and distract them for an instant. Then what you do is you're going to drop the ruler. And hopefully this person will catch the ruler somewhere before it falls to the ground. And the distance, how far fell before you caught it, is going to be a measure of your reaction time. Now remember, distance, this is from way up top in this lecture, is V0, the initial speed, times t, plus 1/2 a t squared. Okay, now what are we doing? We're going to drop something. We're going to drop it. If we drop it, remember, V0, the initial speed, is 0. That means the distance then is equal to, this term goes out because V0 is 0, is just 1/2 the acceleration times t squared. But if we drop it, that just means the acceleration is just g. So the distance it's going to travel is 1/2 g t squared. Okay, so I'm going to move that over here. So d, when we drop the ruler in your friend's fingers, and they catch it after a certain distance, right? So d is going to be distance that the ruler drops before they react and catch it, right? That ruler drops or falls before being caught, being caught. Okay, so we have this d equals 1/2 g t squared. But we want to measure, we want to measure t. Okay, so t is going to be your reaction time, the time it took to drop that far. Okay. So we have to solve this for t. Solve for t, the reaction time. Okay, so let's start over here. D, go slow, is 1/2 g t squared. Now we got to get t all by itself, okay? T all by itself. So let's multiply both sides by 2. We'll go slow, by 2. Okay, 2 times 1/2 on this side goes out. So we have 2d equals g, oopsie, g, that's a g, sorry, t squared. Okay, so now, come on, pen. Why are you being so bad today? All right, so we're going to get rid of the g on both sides. Okay, and what we end up with is t squared, oopsie, equals 2d divided by g. And so if we want t, we have to take the square root. So t is 2d over g square root. And that's going to be your reaction time. Okay, now here's a side note. Okay, so this is the reaction time. Now in the lab write-up, in the lab manual, this is what they do, and it looks a little confusing. So let me try to help you. Okay, you can write, well, D, when you measure D, it's going to be in centimeters. Okay, the rule is not going to move, 2 meters, 3 meters. So we're going to do G in centimeters, D in centimeters, okay? That means we're going to take G to be 980. We're going to do the centimeters per second squared, okay? So what we have is T equals 2D over G square root, okay? Now watch, we're going to write this as 2 over G the square root, and then you can multiply by the square root of D, okay? Well, it turns out the square root of 2 divided by G, if we do centimeters, this is the square root of 2 divided by 980 centimeters per second squared, the square root. And they work this out, okay? And this comes out to 0.045. Okay, they worked that out. I'm leaving the units out for now because it's gonna be seconds, and then the centimeters go out with centimeters here. If this is centimeters, the centimeters here will go out. Okay, so that means your reaction time, when you measure that length that the ruler falls in centimeters, your reaction time, they simplify it, is this: T reaction time is equal to, we're going to put this square root of 2 over G, 2 over 980 is 0.045. So it's 0.045. And then we take the square root of D. Now, this is the distance the ruler falls, distance that the ruler drops in centimeters. Don't forget, we're doing centimeters. Okay? So we measure that distance that the ruler dropped and multiply by take the square root, multiply by 0.045, and we'll have the person's reaction time. Now, notice again, the reaction time should not be 5 seconds. It means the person's dead if it takes them 5 seconds to respond to a ruler falling through their fingers. So T should be less than a second, right? Should be less than 1 second. Right? Usually it's about 0.18 or so seconds, something like this. So when you do your numbers, you should get something, a fraction of a second. Yeah, it could be 0.2 seconds, but usually a little less than that. Reaction time depends on the time of day. If you had too much coffee, if you're a female, a female thing, time of the month, or whatever else. There's many factors, right, that affect your reaction time. We're not always as sharp as we are at certain times, especially in the morning. Okay, so this is a summary of, hopefully it helped for lab number 2. Okay, good luck. Bye.